Good day, everyone. Today we are going to look into the topic of shear force and bending moment diagram for our theory of structures lecture. Alright, before this we have already looked into the example of indeterminate beam like this one, and we have already selected the method of slope deflection method to determine the support reactions and also the reaction internal forces for the beam. Okay, so just to recap what we have already done before this is our beam, and it has three spans, AB, BC, and also CD. And at point A, we have 5 kilonewton of point load, and between B and C, we have a uniform distributed load of 10 kilonewton per meter. And between C and D, we have a point load of 30 kilonewton. B is supported by pin, and at C also is supported by pin, and at D is supported by a fixed support. So using the slope deflection method, we have already determined what is the internal moment of the at both ends of the members after cutting them like this and that, and this is what we have already calculated. We have MBA of 10 kilonewton, and also for member BC we have negative 10 kilonewton meter at one end, and another end is a positive 15 kilonewton meter, and for member CD we have negative 15 kilonewton meter, and another is 15 kilonewton meter at the other end. So based on this end moment that we have already calculated using our slope deflection method, we could determine what is the support reaction. So I put here support reaction is RB, RC, RD, and MD. So using the equilibrium at the support, we could determine what is the support reactions, and we have already determined based on each member. So we look first at member AB, and from this we have calculated what is the vertical reaction at B, and VBA is 5 kilonewton pointing upward, and together for member BC we have the vertical reaction at B, VBC equal to 18.75, and also BCB equal to 21.25. So using these reactions, we could determine what is the support reaction at B, RB equal to 23.75, and similarly for member CD, with the same procedure, so we could determine what is the support reaction at C equal to 36.25, and similarly we have the reaction at support D, 15 kilonewton, and we also determine the moment at D equal to 15 kilonewton meter. So using all this reaction, we could calculate and produce our shear force and bending moment diagram. So for this session, we are going to look into the detail on how to produce the shear force and bending moment diagram. There are two ways of producing shear force and bending moment diagram. The first one is you look into your member. Each member want a process. So for example, in here we have three members. So you look first into member AB. You produce the shear force and bending moment diagram of AB, and then for member BC you produce the diagram for member BC, and for also member D you produce it, and then you combine them all. So this method, the first one, is better in order for you to understand the concept of the shear force and bending moment diagram in detail. However, as you go through and you have already understood the concept of the shear force and bending moment diagram, so you could always produce the diagram all together, meaning like all the three spans, you produce them together, no need to separate them one by one. However, for this first session, I will go into detail first on how to produce this diagram based on the members And definitely after this, once you already understood how to produce it, then you could always draw it as how you prefer it to be. If you prefer it to be like member by member, you could always do that. Or if you prefer it all together like in a continuous beam, then you could always choose the method that you feel easy for you to understand. Okay. So for the first method, in order to draw the shear force diagram, I look into first the member AB. Okay, so from our calculation, we have determined that for member AB, we have the external force on the cantilever part of A, 5 kilonewton, pointing downward, and from the support reaction, the equilibrium of the member, we got 5 kilonewton pointing upward here, and from the slope deflection method equation, we determine there is the moment of clockwise moment, positive moment at B, 10 kilonewton meter. So the guidance for the drawing your shear force diagram is this one, pointing upward, and downward here is going to be positive. Okay. Now, if you look into the end of A, you will see that the arrow here is pointing downward. Okay, so it is a negative arrow. So here our guidance, if it is pointing upward, is positive. Pointing downward here is also positive. So since that our arrow here, the point load is pointing downward, so it's going to be downward here, 5 kilonewton negative. Okay, and similarly to this one, you have pointing downward, so pointing downward is negative. This is why you have negative here and also negative here, because this is going upward and this is going downward here. So negative, negative. And since in order for you to understand how you can connect these 2 points, because here you already knew 5, you already knew 5, and since it is the pointing down, and pointing up, so it is vice versa of our guidance, positive, so it's going to be negative 5 and negative 5. And how you can connect these 2 lines together? In order to have the slope in shear force diagram, this is our equation. Okay, dV over dx equal to negative W. What is W? Is the loading, the uniform distributed load. So dV over dx negative W. If you have dV over dx equal to 0, meaning the slope is a straight line. Okay, like this one. And if you have dV over dx equal to some negative value, so your slope is pointing downward like this. And if you have dV over dx is a positive value, your slope is pointing upward. So look at now look at the member AB this way. I look into 2 points over here. Okay, so basically this is point A and this is point 1 and this is point 2. If I cut on my beam, so at point 1 there is no W here, there is no uniform distributed. It's basically you don't have any load, so definitely your dV over dx equal to 0. So your slope for that point 1 is a straight line over here. And similarly at point 2 there is also no W, so dV over dx is equal to 0, so your slope also is a straight line. Since there is no load in between of A and B, so you can conclude that between point and B here, the slope is going to be a straight line because the dV over dx is equal to 0. So this is why we connect these 2 points as a straight line together. Now, if you look into member BC, you have a uniform distributed load W equal to 10 kilonewton per meter, and you have the support, you have the end reaction VBC equal to 18.75 pointing upward, and you have the VCB equal to 21.25. So again, we refer to our guidance to prepare our shear force and shear force diagram. Going up is positive and over here going down is positive. So we look into our reaction here. So it is the same arrow going up and going up, so it is positive. So this is why positive 18.75, we put it at the corner over here. And this one going down supposed to be positive, but it is here going up the arrow, so you have positive, you have a negative 21.25. So this is why we put it negative 21.25, because the arrow is different, so it is negative 21.25. How you wanted to connect these two members? Again, you can look into the dv over dx. So right now, if I cut my point into three location, I have location 1, location 2, and location 3. So at location 1, I have dv over dx equal to negative. So our equation is dv over dx equal to negative w. So our w is a positive 10 kilonewton per meter. So you have negative 10 kilonewton. So you have negative 10. Okay. So since this is negative 10, it is supposed the slope is going downward like this. So at point 1, your slope is going downward. At point 2, similarly, you have w equal to positive 10, so dv over dx is negative w, so it is going to be negative 10. Again, at point 2, you have slope going down. And at point 3, similarly, you have w equal to positive 10, so dv over dx equal to negative 10, and again you have a slope going down. So if you see here, there is no other, in other words, there is no other loading other than w pointing downward here. So this is why all our slope is negative 10, and it is all pointing downwards. So you could always draw your line between point B and C to be pointing downward altogether down here. Okay, so this is your shear force diagram for member BC. Now for member CD, you have your end reaction at this is C and this is D. So you have VCD equal to 15 kilonewton, and then you have a point load of 30 kilonewton over here pointing downward, and you have 15 kilonewton at point D. So this is our guidance in order to produce our shear force diagram. Going up and going down is positive. So we look into here. The arrow at point C is going upward, so it is positive because upward and upward is going to be positive. So we have a positive 15 here. How about the point D? It mentioned that if it is going downward, it's going to be positive, but our arrow here is going upward, so it is a negative. This is why we have a negative 15, because this is 15, so negative 15. This is 15, so this is 15. And we have going downward of 30 kilonewton. So how we could join these two points over here? Since if I take location 1 and location 2, and at location 1 there is no uniform distributed load, W is 0, so your dV over dx equal to 0. So this means that the slope is a straight slope. So you can connect these 2 points using a straight slope. You have a pointing downward of 30 kilonewtons, so 15 minus 30 is going to be negative 15. So going downward, negative 15. And then between these 2 points, from the point load and D, also you do not have any W equal to 0. So dV over dx equal to 0, and the slope is a straight line. So between these 2 points, you can connect them with a straight line. So this is the shear force diagram for member CD. Now you have already determined a shear force diagram for member AB. Okay, so for member AB here, and you have already for member BC, and you have a diagram for member CD. So you could just connect them together. So this one is for the member AB. And the values, do not forget to put on all the values, the important values here. And this is for member for member BC, and also this is for member CD. And you just have to put all the values and just connect the other shear force diagram for all members. And if you have diagram like this one, and you wanted to determine what is the distance between this point B and the location where the shear force is negative, you could always do the ratio between the distance and also the shear force diagram. So x over 4 minus x is equal to 18 divided by 21.75, and you will have x equal to 1.9 meter. Okay, so you knew from this point, from B until the location of the zero shear force is going to be 1.9 meter. So this is how you could draw your shear force diagram for our continuous beam. Okay, so let us see how you could draw your bending moment diagram for our member. Similarly, I choose first here to draw it member by member in order for you to get a clear idea of how to draw your shear force and bending moment diagram, because you need to have a full understanding to get the diagram here in order for you to have an easy process of drawing this diagram when you enter to your frame structures. Okay, so you have member AB, and this is your shear force diagram for member AB. So this is your end moment for member AB. So you have 0 MAB, and also MBA you have 10 kilonewton meter. So this one you have already calculated using your slope deflection method equations. Okay, this is our guidance in order for us to draw our shear force diagram. If you have a moment at this end, positive moment, clockwise moment, and at this end you have a negative moment, anti-clockwise moment, so your moment here is going to be positive. Okay, before this we have the guidance of shear force diagram to be arrow up and arrow down to be positive. So for shear force for bending moment diagram, if it is pointing like this, the arrow is going to be positive. In other ways, if you have a smiley face, okay, so this is like smile, going up, and it's going to be positive, right? So this is our guidance to draw our bending moment diagram. And in order to get the slope between the members, if for shear force diagram we have dV over dx equal to negative W, okay, so for the bending moment diagram we have dm over dx equal to negative v. So v is the value of shear, so this one is the value of the loading. Okay, so I repeat, for bending moment diagram, in order to get the slope we have dm over dx equal to negative v. V is the shear, and if your the value of your dm over dx equal to 0, the slope is a straight line. Okay, if the ratio equal to a positive value, the slope is going upward like this, and if the dm over dx is equal to negative, the slope is going downward. So similar with the shear force diagram, if the value is positive upward, negative is downward. Okay, so let us see our member AB, and between at point A and at point B you have 0 moment at point A, so this is why at point A we have 0. Okay, 0, 0. And at point B we have a clockwise moment of 10 kilonewton meter. However, our guidance says if the direction is anti-clockwise, it's going to be positive. Here direction is clockwise direction, so it's going to be negative. This is why 10 kilonewton, negative. Okay, because the direction based on our guidance should be anti-clockwise, however direction here is clockwise, so negative 10. So you have 0 and negative 10 for your bending moment diagram over here, and in order to connect these 2 points, okay, we use dm over dx equal to negative v, and if we have 2 points taken in our shear force diagram here, for point 1, okay, for point 1, dm over dx equal to negative v, so our v is a negative. Okay, negative 5, so it is negative 5 over here, so our slope is going to be positive 5 slope is going upward. Okay, at point 2, similarly, you have dm over dx equal to negative v. So how much is our v at point 2? Is equal to negative 5. Okay, so negative 5, it make it positive 5. The slope is pointing upward as well. This is why for these 2 points, you have a slope pointing upward. Okay. Now between member BC, okay, member BC, you have end moment of 10 kilonewton anti-clockwise and another one clockwise 15 kilonewton meter, and you have a uniform distributed load of 10 kilonewton per meter, and this is your shear force diagram. You have 18.75 and you have negative 21.25. So this one you have already drawn from your shear force diagram before this. And we look into our guidance to produce bending moment. It mentioned here if you have a clockwise at this angle direction point and you have an anti-clockwise at this end, is going to be a positive moment. So if we look into this, we have a counterclockwise at this point, 10 kilonewton meter. So since it is opposite direction of this guidance, so this is why you have negative 10 over here, and for the other end you have clockwise. However, guidance said anti-clockwise is positive, so again you have a negative 15. So this is why here negative 15 kilonewton meter. So please be very careful for shear force and bending moment diagram. Upward is a negative, okay, and down here is positive. However, for your shear force diagram, upward is positive and downward is negative. Okay, so please be very careful in these two. So for this bending moment diagram, you have negative 10, you have negative 15 at two ends. How you're going to connect these two points? If you want to go into details, so I cut them into the 6 locations. Location 1, location 2, 3, 4, 5, and 6. And between location 1 and 3, if you see here, if I at location 1, if this is 18.75, so estimated for location 1 is going to be 16 kilonewton, and dm over dx, I will have negative v, so v is 16, positive. Okay, positive. So I will have my slope, negative slope going downward. Okay, and how much is the degree of my slope is negative 16. At point 2, somewhere around here, my v is going to be 14. So again, I will have a negative slope going downward, but the degree of my slope is lesser than the previous one. From point 1, I have the degree is 16, but at point 2, my degree of slope is 14. So if I have 6 at point 1, my slope is a little bit steeper like this. At point 2, my slope is a little bit lesser steeper compared to point 1. At point 3, again, it is getting less steeper because I have negative 8. So again, pointing downward, but this degree of my slope is becoming even lesser, 8. At point 4, I do not have any W here. I do not have my V is equal to 0. So due to this, my slope is going to be a straight line because dm over dx equal to 0. So this is why at point 4, I reach to the point where it is a 0 slope. It is a straight line, and the moment I go to point 5, since that my v is negative 8, okay, because this part is negative, so negative 8, then I have my slope pointing upward because dm over dx equal to positive 8. So this is why at 5 I have a slope going upward, and at 6 similarly, I have negative v, so negative at 6 is going to be around negative 16. So I have negative, it makes it positive, and my slope is going upward. Okay, my slope is going upward like this. It's a bit steeper compared to 0.5. So this is why I have a slope from steep, okay, a very steep one, I get to a lesser steep, and then let's just step until I got to the point where it is a straight line, and then I go up and step back again. So this is the shape or the slope of my diagram. Between -10 to -5, I have this slope here, smooth like that. So between for member CD, all right, you have end moment at C, counterclockwise, so 15, and then another end moment at D, clockwise direction of 15, and I have only one point load between these 2 points of 30 kilonewton. And if I look into my shear force diagram, I have this one. I have 15 positive, and then another one here. So if I look into the guidance of drawing my bending moment, smiley face is always positive. So I have here, since the direction of point C is opposite direction, so if it is clockwise, okay, is positive here, but this one is counterclockwise, I will have -15. Okay, so -15. So this one is also this one is 15 value, and the direction also is the opposite direction. This one is supposed to be counterclockwise, but this is a clockwise direction. So again, I have a negative. So this is why -15. So at this point, I have 2 points here, -15 kilonewton meter and -15 kilonewton meter. And how am I going to draw the line between these 2 points? Okay, whether it is going to be similar with the previous one, I have a curve like this one, or I have to make it like straight line like this. If you look into the the equation that we have, I will have dm over dx equal to -v. So if I cut my shear force diagram here into 6 points as well, in order for you to imagine it, and if you see between point 1, the 2, and 3, I do not have my V is here, my shear force here is all positive 15, right? So if I can get my dm over dx negative V, so it's going to be, since my V is 15, so -15, so the slope is going downward. However, between point 4, 5, and 6, my shear is a -15 altogether, so my dm over dx is negative times -15. It makes it positive 15, so the slope is going upward. Okay, there are no other than these two values, so the slope is straight line because the degree of slope is similar between the points. So before this, for this one, you have a different slope for each point. You have 16, you have 14, 8, and also similarly with this one. This is why you have a slope with different degree of steepness. You have first very steep going downward, and then less steep, and then you have horizontal. So you have something like a curve in the end like this one. However, for member CD, all the slope is similar degree of steepness. You have 15 and 15. So this is why you could always draw a straight line until you reach to a point where there is no differences between them, and you go up again straight like this. So this is the bending moment diagram for member CD. Okay. Now, once you have already determined what is the bending moment diagram for member AB, BC, and CD, you could always join them together like what you have done for your shear force diagram. Okay, this is going to be like this one. So this is our beam, and this is your shear force, the diagram that you have already determined one by one, and then you combine them all, and this is the bending moment diagram that you have already produced before this. So the next step is to draw what is the deflected shape of your beam. Okay, the deflected shape of your beam over here. Now, how to draw your deflected beam, the shape of your deflected beam. At support, there is no deflection, so zero deflection, and negative moment give concave up direction of the members, so concave up is like this. Okay, And positive moment give concave down like this one. So positive moment smiley, negative moment a sad face. Okay, so how you're going to do this, you can look into here. And our bending moment diagram, this is the negative moment. So negative moment has the sad face. Okay, and positive moment here, this is the area of positive moment, have a smiley face. Another one is the negative moment. Okay, the shape is like this, and positive moment again is smiling, and negative moment is a sad face. Okay, so this is the deflected shape of your beam based on the bending moment diagram. So how you can draw it, and if you see for this area, okay, it is until this point. So meaning from point A until somewhere around here, a few meter distance from the support, you have a sad face, a negative moment. Okay, so you draw it, this curve until here. Okay, so like this one. Now for between this point and this point, you have a concave like this one, concave down, a smiley face. So it should be going like this, the deflection. Okay, smiling location. And from this one, you have a negative moment, so it is a sad face like this. So you have a deflection shape of this way between this point to this point. So between this point to this, you have a deflected shape like this one. And here you have again a deflected shape like this until this. Okay. And from here to here, since it is a negative moment, you have a concave like this one, and you draw it like this. Okay, so basically your deflection shape of your beam is going to be like this one. Okay, so you have a deflected beam shape like the one that I have drawn in here. So if you wanted to see how your beam deflected, but due to this point load of 5 kilonewton and uniform distributed load of 10 kilonewton meter, and another one in here, so the deflection is like this. And be very careful at the support, there is no deflection, so you have a little bit of straight line here before it ends to this one. Alright, so this is what you have to do from the beginning to the end. You have an indeterminate beam, so you use the slope deflection method to get all the reaction, and then you can draw your shear force diagram, you can draw your bending moment diagram, and you have the deflected shape of your beam. Okay, so in order to get what is the value of this one and this for E and F, what you can do is that you could have the value, okay, at E, the MB equal to plus the area of shear diagram between B and E. So you can take this one, okay, the moment at B plus the shear force diagram of this one. So you can get E equal to this. Similarly for this one, you have the 15, alright, so the moment at C plus the area of your shear force here between these 2 points. Then you can have your F equal to positive 15. Okay, so similarly with like this one, I have already measured. And as I mentioned to you, this is like the method of drawing your shear force and bending moment diagram based on member. So at this example, I choose to draw it point by member by member in order for you to understand in detail how the slope between two points is being produced, and whether it is going up or whether it is going down or whether it is a straight line. However, as you go through with more examples, you could get more familiar with this method, and you do not have to do it member by member. You can always remember, like if there is no force or there is no load, and it's going to be a straight line. If there is a uniform distributed load, and it's going to be like a triangle shape or like a square shape like that. So it is based on your experience in order to get it. But if I show it to you, Okay, for example, if we look into one here, okay, so if I draw it based on the continuous beam, I'm sure you have also already learned this method during your mechanics of material, because this is the simplified method for it. If I have a beam here and I have a point load of 5 kilonewton downward, and I have my support reaction of B, so you have already calculated your support reaction of B, 23.75, and I hope I have my support reaction at C, 36.25, and I have a point load of here 30 kilonewton, and I have at my point D support reaction of 15, and also my moment at 15 kilonewton here, and here I have 10 kilonewton per meter. Okay, so this one is 30 kilonewton, and this is 2 meter, this is 4 meter, and this is 2 meter, 2 meter. So this is my force diagram. If I wanted to calculate my shear force diagram, it's going to be very simple. And I have, if it is pointing downward, I will go down negative. Okay, so -5, because it is pointing down in between point A, B, C, and D. So between point A and B there is no load, so I go straight. Okay, and this one is pointing up. Pointing up is positive, so the value here is going to be -5 plus 23.75. So I go up here, so -3 and -5 plus 23.75. I will have the value here of positive 18.75. Okay, and I have a uniform distributed load of 10 kilonewton per meter for 4 meter distance, so I have to minus 18.75 minus 10 times 4. So if I minus it, I will have a value of -21.25. So I go down here and I will have here -21.25. Okay, and I have here my support reaction going up 36.25, so -21.25 plus 36.25, I will have to go up. Okay, I have to go up, and I will get 15 the value, and between this point there is no load, so I got straight line here, and the moment I reach to this point, I have to minus it, the 30, because going down, so it is going to be 15 minus 30. I will have -15. Okay, -15, and since there is no load over here, I go straight line, and I have another 15 going up, so -15 plus 15 here, I will reach to 0. Okay, and so it's easy as that. You can look into here. This is my shear force diagram. In order for me to draw my bending moment diagram, okay, so it is the area of shear force diagram. So I have to calculate what is the area over here, what is the area over this one, what is this area. I calculate what is this area and what is this area. So if I calculate this area, -5 times 2, I will have here to be -10. Okay, -10. I'll make it a bit clear for you. So if I put -10, the area over here, and since this is we have calculated to be 1.9 meter and this one 2.1 meter, so I have something around positive, because this is positive 18.75 times 1.9, I have something around positive 17.8, and another one here, since it is 21, -21.5 times 2.1 triangle divided by 2, I will have here -22.3, and this one is positive 15 times 2, I will have this area to be positive 30. Okay, and this one is -15 times the distance 2, I will have -30. Right, so if I draw it, we knew that for bending moment diagram, negative is upward. Okay, so I have -10 here, then from this point to this point I will have negative 10. Okay, and since there is no other, this is the triangle. Okay, so I have a straight line. Okay, straight line, and since this one from here to here it is triangle, so I need to minus negative 10. Negative 10 plus the area over here plus 17.8. I will have somewhere around like this a curve. Okay, positive 7.8, and then I have to here negative 22.3, so meaning 7.8 positive minus 22.3, I will have somewhere negative over here. Okay, negative 14.5, and then I will have to plus the 30, so I will have something like this one here. Since it is rectangular, so it is going to be a straight line, so it's around here 15. Okay, and I have to plus, I have to minus 30, so 15 positive minus 30, I have a straight line of negative 15. Okay, negative 15, and since this one is the clockwise moment, positive 15, so this is why negative 15 plus 15 here, I reach back to 0. Okay, so this is your bending moment diagram for your continuous beam. You could always opt to draw it continuously based on the area of your shear force diagram, or you could draw it part by part, just whichever the method that you feel it is convenient and you could understand it well. These are the two methods. Okay, so that's all for our shear force and bending moment diagram. I hope you could have a good understanding, and when we enter to your example of frame structures, you wouldn't have any problem in order to draw your shear force and bending moment diagram for your frame. Okay, so good luck and thank you for your attention.
انضم معنا الآن واشترك بالقناة ليصلك كل جديد. YSAG، معا نحو مستقبل مشرق.